So I'll start recording.
Hi, welcome to the last discussions in complexity this semester. We're happy to have Dr. Sean Bergin talk today. Sean has training as an anthropologist and archaeologist, and has done a variety of things over time, trying to understand the way in which individual decisions and actions can produce large-scale emergent patterns, both in the past and also in the present. And so I think he's going to talk today about a variety of modeling efforts, both dealing with this as diverse as the spread of agriculture and response to hurricane warnings. And so it should be a fun and interesting talk. So I'll pass it on to you, Sean. Looking forward to hearing this.
Thank you, Michael. Thanks for the introduction, and thank you all for being here. Today, I'm going to start off talking about a tiny bit about my background, and then a little bit about my theoretical interests. And then I'm going to focus on two of my sort of major ongoing projects that I'm involved with. So similar to a lot of the faculty in SCAS, I didn't start out in complexity. As Michael mentioned, I began my training as an archaeologist, which is a subset of anthropology. And I think today, most of the time when people ask me to define myself, I usually use the term social scientist. But as a young graduate student, I worked in Jordan on early agricultural archaeological sites, and throughout my career then moved westward to do a lot of research in Spain as part of the Medlens Project. And more recently, I've been working in the Western US in Washington State. And as Michael said pretty eloquently, my interest is in creating computational models of socioecological systems, both in the past and in the present. And more of my, a lot of what I'm talking about today is going to be using data to try and not necessarily validate the models, but something close to validating the models anyway. So I put this image in as a sort of tongue-in-cheek joke, just to show, that my master's level, this picture on the left is from my MA, where I was looking at microscopic analysis of the edge of stone tools. And then the image on the right is from my PhD a few years later, doing this complex agent-based model, looking at the spread of agriculture from Italy to Spain. And you can tell, obviously, I made a pretty dramatic intellectual shift there. And a lot of that comes from my involvement in the Medlens Project. The Medlens Project was begun with the intention of understanding long-term environmental effects of human-environment interactions in the Mediterranean. Excuse me. The project developed multiple landscape models of human decision-making to understand the dynamics of subsistence level farmers. And while I think it was more geared towards prehistoric level farmers, it's a lot of the lessons and models are applicable to modern farmers as well. And I'm not going to talk in detail about this project because Michael Barton has already spoken about it in his talk. But I do want to say, that I'll just describe it as one of this first, if not the first project to really use complex systems theory to understand human and environmental interaction. And this project conducted archaeological and paleo-environmental fieldwork, in addition to using simulations to sort of, in concert, try and understand whether or not simulations are actually producing realistic results, and to compare some of the archaeological and paleo-environmental results to the simulation. The second and related project that I was also involved with as a graduate student, and I'm still involved with today, is the Compsysnet. Compsys is a science gateway whose goal is to improve the development and accessibility of models, of socioecological models. And one of the main features of Compsys is the development of a model library where people can archive their code. And it's not just a place to dump your code. It's a place to provide detailed documentation that should persist. And there is a peer review system to help people, to encourage people to do a very good job of documenting their code and in the code itself, and providing narrative documentation. And my role in Compsys is part of the education team. Compsys for a long time has been running winter schools to teach people about socioecological modeling. And now we are developing content to help people use FAIR practices, which essentially responsible coding practices to provide your information, to provide good documentation, how to choose a good license for your software, and all these types of things, as well as tutorials on GitHub and containerization. And the hope is that in maybe a few months or a year, there will be some online tutorials that you can take to sort of teach yourself, kind of like a individual MOOC, to teach yourself some of these skills, and maybe even get a certificate saying that you know these skills fairly well. I also want to quickly mention a project that I'm finally finished with. Recently co-edited a volume on modeling, using computational models to understand the transition to agriculture. This was the result of a conference in Barcelona a few years ago. And those of you who have worked on books or been editors of books can understand that, you know, it took a lot longer than I thought, but it feels very gratifying that this just came out this spring. Even though it says 2021, it actually came out in 2022. This is not meant to be an advertisement, so if anybody is interested in finding this volume or reading some of the chapters in this volume, please let me know. There's a great chapter by Michael Barton on some of the more recent Medlens work, a number of interesting approaches to modeling the past, and again, I'd be happy to provide anyone with that. This slide is sort of meant as an advertisement. One of the projects that I guess this was about a year ago now, but collaborated with Claudine Gravel-Miguel to make a tutorial for agent-based modeling based on the Game of Thrones series. I should put out there right now that I'm not a big Game of Thrones giant fan or anything like that, but we thought it was be a fun and an accessible way for people to learn some of these agent-based modeling techniques. So the tutorial is extremely detailed, goes line by line through the code, and starts off with a model that NetLogo provides called the wolf sheep model. And we sort of document how we changed that model into a model of the Game of Thrones series, which includes this landscape from the novel, so therefore we're showing people how to import GIS data, networks between sort of the major houses of the series. There are these families that control large areas, and you can see in this image here that is represented as well. And also creating different types of agents. There's dragons eventually, and White Walkers, which are sort of a zombie thing that comes and attacks. And if you're interested, the actual code of this model is available on Compsys, and there's a link there to the more detailed tutorial. So I'd encourage you, or if you want somebody's interested in learning just about agent-based modeling, to use this tutorial, because we're very proud of it. So the first project that I want to talk about in detail is the Central Cascade Alpine Land Use and Fire Project. My colleague is Grant Snicker, who is a graduate of Arizona State as well. We began this project with the goal of developing an understanding of the socio-ecological history of the Central Cascades. So it's this area in this little black box in the inset on the image, east of Seattle. Research in this region is really underdeveloped due to the region's remote location. These are really high elevations, and sort of the idea that people just see this area as marginal, sort of a no man's land that sort of separates cultural centers. So there's just, there's people on the west side and there's people on the east side, but there's of course nobody in the middle. But as often is the case, areas that are remote or unused by Western settlers now get cast as undisturbed wilderness. Yet, recent research in areas to the north and the south has revealed that these what are called alpine and subalpine ecozones contain a long and rich settlement history spanning much of the Holocene. So over the last 10,000 years, people have been using this area more than likely. Alpine and subalpine ecosystems are a really unique ecozone that occur, I don't know what, not only in the Cascade Range, but very few other areas. They're meadow vegetation communities limited to elevations above 4,000 feet and sort of are at the margins of tree lines. So with this project, we're hoping to gain a perspective of how these areas were used through time and whether or not they were managed in any way. The main culprit might be a fire, and sort of identify the history of occupation, pre-contact and post-contact. So to these ends, we've begun to synthesize evidence that has been compiled and collected as a way to understand the long-term legacies of land use in the region. So just to give you a brief idea, this image on the left here is the extent of national forest land, which has been conducting research. It's been conducting research into the settlement history, which really archaeological research for 50 to 75 years, depending on the location, and compiling a huge amount of data. So you essentially have this almost, I don't know, endless, seemingly big data collection on land use. But a lot of it is, well, all of it is definitely not in the public record because these site locations need to be kept private so that they're not disturbed by the public. And a lot of it is also in paper form. So you can see on the right here, this is a typical site record from the area that we're interested in. And it has a lot of great information. I should say this is also a fake version of a form because we don't want to provide people with actual information. But you can see that there's a lot of geographic information about potentially the time period, the size of the site. There's a lot of useful information that we can use to understand how this particular location might have been used through time. So a lot of the area that we're interested right here is part of the Cle Elum Ranger District. So with the approval of the Cle Elum Ranger District, which is part of the Okinawan-Wenatchee National Forest, we are allowed access to their site records to digitize the documents, to scan them into PDFs. We scanned a total of 793 sites and provided the digitized copies to the Cle Elum Ranger District. But here's where we sort of run into sort of this is a problem we all sort of encounter in different parts of our research. Do we do something the simple way, whereas we could go through all these PDFs and transpose by hand all the information into a database, or is there a quicker way to create a tool that might actually take more time to build in the long run, but might then provide us with more accurate results? So what we decided to do was develop an R package with the goal of extracting information from these site forms. So number one, so that we don't have to, and so that other districts, other ranger districts could then use this tool and extract the information themselves, or we could use it in other locations to sort of gain access to all of this environmental history and all these archaeological sites, and then be able to use it to do other analyses, mapping and looking to see land use through time. So we created Archaeo SRP. It was originally named SRP, but of course, there are millions of R packages out there, and there already was an SRP. And so the Archaeo SRP, it's an R package that extracts information from these archaeological site records, which are have to be stored as PDFs, and then all this information is read in by the program and stored as a data frame in R. So then you can then do further analyses. The package is provided for the use and for modification by other districts, although I would ask you not to download it within the next week, because recently realized there was an issue. It works fine on my computer. The only issue is that it's not properly saying what packages it needs to go with this package. So we used it to scan and record information from the 793 sites. Oh, and I should also say too, for each of these sites, some of these site records are 2 pages long, but some can be 50 pages long. People have gone back and done further analysis on specific sites. So this is just a huge amount of information to have to go through. Adding to the sort of complexity of storing this information is the fact that these site forms change through time. So there's a standard form for 5 years, 10 years across different states and around the country, but it gets modified. And so we ended up having to identifying 19 different site record types, which adds a sort of another level of difficulty. So the way this package works is that for each of these site types, we first sort of identified a way for the program to figure out which form it is. So form number 1 has the phrase cultural resource site report on the top. Form number 2 might say something completely different. And then we use sort of what I term as a bookend approach, which is just, what is the word before the information that we need, and what is the word after it? And parse out parse out all the information that we want. So here you can see we're grabbing the site name, geographic information, the UTM zone, easting and northing, the period of use for the site, and site use. And there's a number of other pieces of information that we record in, so that we can then we can understand how the site was particularly used in time and how it fits into the greater context. So I should also mention we use a number of other packages. So we used Tesseract, which is a program that automatically will scan a PDF and turn it into text so that is selectable. We use OCR, optical character recognition. And that just gives you a giant list of words, which is then what this program parses. So the idea too is that all these procedures that sort of find the word are available, so that if somebody wanted to come in and use it for a different purpose, they wanted to identify new site types, they could. So hope is that people will take this tool and expand upon it. So here's just a little taste of some of the information we were able to extract. We mapped pre and post contact land use information from all these scanned documents. Each cell is assigned a weighted probability that it belongs to a period based on the artifacts in the assemblage, and then mapped out. Because we're trying to protect the actual location of sites, we're using 1 kilometer grid squares, so there can be multiple sites within a square. And you can see in general that there's a much more extensive land use for the post-contact area. But in mapping all this information, we really realized how few surveys were actually conducted in this area. So in other words, not all these empty grid squares are necessarily empty. So with that in mind, we then started a survey project to better understand what is going on in sort of the upper elevations, these alpine and subalpine areas. So the adjacent high elevation areas of the Okinawa-Wenatchee National Forest's Alpine Lakes Wilderness area is even less studied than this area that I showed you earlier. So this top image is intensive surveys near the Cle Elum Ranger District. But these upper elevation areas have been studied approximately 1%. Because they're designated as wilderness areas, they are essentially meant to be untouched by people and by researchers, and it requires large amount of forms and special permission to even work in these areas. So the project is now going to conduct some surveys in these alpine and subalpine ecozones, and not just because nobody's done work there, but because we actually have ethnographic and historical accounts that, at least in some of the upper alpine areas in the vicinity of Mount Rainier, which is to the west, that these areas were visited by hunter-gatherer bands pretty regularly and used for communal berry harvesting, especially huckleberries, which is that image in the middle there. And that these areas were intentionally burned, according to the ethnographic record at least, to prevent tree encroachment and to encourage these berry patches to grow back. So some of these locations have been identified in the northern Cascades. And so we're really interested to see if the practice is continuing here in the central Cascades, and really to see sort of if there is a history of management pre-contact. So we conducted a short pilot study last fall of survey in these areas, and hence the image on the right there. And we're going to do, we plan to conduct more pedestrian surveys. And once some locations that people were occupied, some archaeological sites are identified, to do some coring to understand how long these sites were occupied, or the depth of the cultural material. And to take some paleoecological samples, really. That's the more interesting part, I think, is that we're going to try and understand, look for charcoal, look for evidence of burning in these areas, and try and create a localized record of the vegetation and fire history. Oh, and I should also mention too, we did actually find artifacts. These areas are not empty of people. I've, again, embargoed from showing you pictures of artifacts, but there are artifacts up there. People were there, which I'm sure comes as no surprise to most of you. So the final project that I'm going to talk about today is the CHIME agent-based model. It's an agent-based model meant to help us make recommendations about hurricane forecast dissemination and human decision-making in the face of hurricanes. This project, I should mention too, that not only the collaborators, Michael Barton, Rebecca Morris, and Joshua Allen, but those of you who know Josh Watts, who was a member of ASU as well, he did much of the programming on the earlier versions of this model. So a lot of this work comes from him, or is at least based on, in large part, on sort of his shoulders. So weather prediction, communication, and decision-making are interconnected components of a dynamic coupled natural human system. And when hazardous weather occurs, multiple types of actors interact to create and interpret and use forecasts and understand weather warnings and other risk information. And hurricanes aren't going away. Just a few days ago, there was an article in NPR predicting that this hurricane season was going to be more active than usual. And a number of studies have attributed the rise in hurricanes and the length of seasons and the intensity of the hurricanes themselves to human-induced climate change. And unfortunately, that is not going to change quickly. So the idea behind this model is that we can use it to investigate hazard information flow and decisions based on storm information. And this is complicated by a number of factors. Not everybody makes the correct decision. The information they get may be incorrect, whether it's out of date or there is a previous president drawing circles on the map. People can still make the wrong choice even with perfect information though. And information these days comes from a much wider variety of sources, everything from Twitter to Facebook. And also location plays a significant role in these decisions. And so, are you on the coast? Are you in the direct path of the storm? Are you, in an apartment or a small house? There are a lot of other externalities that play into these decisions. So the CHIME ABM is a net logo model available on Compsys, by the way, that begins with a hurricane 5 days from the U.S. coast. We've used both the Gulf. We've done modeling for Texas, but most of our research has been on Florida. Somebody could easily implement another location and using this model though. So the model actually uses real hurricane forecasts and models the environmental conditions and includes this GIS data, which I think is crucial for understanding how people are going to behave based on their location. So the complicating thing about these forecasts is that they change every hour. And so, whereas a hurricane might be predicted to hit the east coast of Florida, suddenly, 24 hours later, and now it's going to hit the central part of Florida. And so the hourly forecasts are a key piece of modeling this system. So in our model, there is the citizen agents. They're the people who are making the decision. I think I sort of envision them as they're really a household. There are public officials that make decisions about evacuation. And we have different types of broadcasters and media aggregators that are meant to disseminate the information to the citizens. So the National Weather Service has a new forecast, and then it is broadcast and through the broadcasters. And you can see all these interconnections right here. So they're getting information from a lot of sources. And each hour, agents decide whether or not they need to take some action in the face of this hurricane. Do they need to evacuate? Do they need to take a protective action of some sort, like boarding up their home? Or do they do nothing? Or they can also, I should add this one, they can also start essentially checking the forecast more often, because they don't always update information from broadcasters, just as if you don't sit there and hopefully watch TV and update yourself on the forecast every hour, especially when a storm is far away. People are checking the information less frequently. So as I said, I think the location of these agents relative to a storm is crucial to understand their decision making and just understanding sort of the pattern of evacuations. So the model itself allows people to just be dispersed throughout Florida. We also have a way of clustering people based on population density. And more recently, we've added in the ability to distribute agents based on census data. And so, and a practical matter, of course, is that you can't have one agent per actual person as recorded by the census. And so the way we approach that is by essentially modeling the population, creating the number of agents based on the number of people in a proportional way. So if we decide, there's going to be a 10% representative sample, that means, if there's 100 people for real in a particular census tract, then our model will represent them with 10 people. And that information isn't just the number of people, it also includes basic socio-demographic information. So the age of the people in the household, number of people, their wealth, and a bunch of really interesting other factors, which I'll talk about in a minute. And all these agents then are connected by a random scale-free network. So on the left is going to be a video of a very sped up video of a Hurricane Irma coming through that gray line. And you can see as it runs, these white flashes, which I worry now I need to give people a warning for or something in case of seizures. But the orange people, the people who've turned orange have decided to evacuate, and the other agents here that have turned green have decided to do a protective action, and agents that are blue have decided to do absolutely nothing. So as I mentioned, the model runs on an hourly schedule. The forecasts are updated. The officials then make decisions about evacuation. The information goes to the broadcasters and the aggregators, and then the citizens make decisions based on that information. So here you can see again, the hurricane coming through. I think this, I don't want to go through this particular slide in detail, but I think I wanted to show it to illustrate the complex decision-making that occurs for these agents. They're collecting information, not just from one forecaster, but from their environment. Is there extreme winds occurring outside their window? What are their neighbors doing? They're weighing information from other citizens, and they're changing how they process that information constantly on an hourly basis, but also they might, like I said, be updating that information more frequently. So this here is sort of represents the information that comes out of this model. So we have the information of the agents themselves, what they decided to do, and also the timing. So this is one thing I haven't mentioned yet, is that timing is also this crucial factor, and that some people don't need to evacuate quite yet, and some people might have, at least in the model, could be evacuating too late. We don't want agents to be getting out of the path of the hurricane right as the hurricane is hitting them. And so timing is actually a crucial element to understanding the evacuation of the citizen agents. So up until recently, this was sort of our sort of standard results. It passes the looks good test, I think, as people use that phrase, or the looks pretty good LPG. But we didn't have a way of sort of evaluating how accurate this model really is. And so just recently we have been able to, we've been given access to a data set from cell phone location data that from Cubic, which is a personal, it's a data broker. Whatever your feelings about data collection and privacy, this is one of those examples where this data is really useful and can do some good. So what you see here is just sort of the information that they gave us, which is that for us, it's been anonymized, and all the way down to down to frequencies per county. So each of these lines represents the amount of people that evacuated. And I want to also point out, because it's going to show up in a lot of slides, that this giant line here is the Everglades. And in future research, I think I'll be taking out the Everglades because it sort of skews everything. But the interesting factor is here is we have not just based on a cell phone's area code, but based on how long people spend in a particular county, that is designated as their home county by Cubic, and then we know how many of them have left that county as the storm is approaching. So here, the 6th through the 11th of September is the time period of our model, and so now we actually have data to compare the evacuations of our model to real life evacuations. So here is is a map of that difference. So the areas that are sort of tending towards red, and the Everglades, by the way, is that southern part of Florida, which you should ignore. But these areas tending towards red are areas where more people evacuated compared to our model. Areas that are white are sort of the most accurate. We're either spot on or very close to it. And these areas that have sort of this light purple, the agent-based model is actually predicting more people evacuated than occurred. And so one of the interesting things to note here, and I have to credit Michael Barton because I did not see it at first, is that at least some of these areas, these purple areas, are centered on urban areas that are the southeast black. All these black dots are some of the major urban areas. The southeast corner is Miami, and on the left is not St. Augustine. I can't remember right now, but is one of the major other urban areas. And that area on the left, by the way, is also where Irma eventually hits. So that last slide was the final comparison, right? So it's after all the days of evacuation, this is how our map compares to the actual number of people evacuated. But as I said, timing is also this other crucial factor. So I say this later too, but I think I have a hard time sort of grasping, are we evaluating timing or sort of the final product of evacuation? And I think the answer is probably both. But so this is a short movie on the left here. This is the first day of evacuation, and you can see it's going to go kind of slow, I think. Maybe. Oh, it is moving. Okay, so now it's changed to the 8th. And you can see on the 9th, all of a sudden, the agent-based model over-predicts everything, and especially for those that area on the West Coast, and the 10th and the 11th, and that's the end, and I think it'll restart. And so when I think this image really makes me want to go back and see, and because I suspect that giant purple spot, for lack of a better way of saying it, that moment when the ABM overpredicts the evacuation, I think it might be tied into when the forecast changes. So the forecast for Irma itself is shifts to the west side much more. And I think in our model, the agents themselves are seeing this new forecast and immediately evacuating much more than they did historically. So as I mentioned, besides using census information for locating agents, we also have looked at it as a way of better predicting the decisions of our agents. So just in a sort of a very simplistic way, maybe, but the idea is that access to a vehicle, if you don't have a vehicle, you're less likely to evacuate. And so we're using the census data to give agents that characteristic, whether or not they're likely to have a vehicle or not. And if they don't, they're less likely to leave. Obviously, if you're using food stamps, that doesn't mean you can't evacuate, but it may be a good indicator that you don't have the economic means to evacuate and that you might be less likely to evacuate as a result. Do you have kids? A lot of studies have suggested that parents with kids are much more likely to evacuate. I know if it was me, I would personally be much more likely to evacuate because of my children. Oops. And finally, are there adults over the age of 65? Usually, Florida does have a large elderly population. And so the idea is that adults over the age of 65 are probably much less likely to be able to leave as a result of an oncoming hurricane. So I tested out each of these census factors to see how they might affect the results that we've got. So here you're looking at the evacuation based on whether or not people have a vehicle or not. And as you can see, it didn't change things all that much. It's very hard to look at these results because of all the shades of pink and determining, what is red and pink. But so I find myself looking more at where the agent-based model over-predicted. And so at least for Miami, that actually did sort of change things and to more agreement with the real results. And I think the conclusion to sort of draw from that is that is actually makes sense, and that in an urban area, people are less likely to have a vehicle. And so that actually might be a useful factor in determining what they might be doing. Here is the information for the food stamps, which produces very similar results to the previous one. And I think that sort of makes sense in that both of these are economic factors, and people who essentially have less money are less likely to evacuate. Here you can see using the census factor of people who have children being more likely to evacuate, and that really skews the results, I think, poorly. The agent-based model overpredicts evacuation for large amounts of Florida, especially in these urban areas, but even up in the Panhandle as well. And finally, the census factor of people who are over the age of 65. This is the only one to sort of, well, the only map that has no agent-based model over prediction, and in general has the best agreement with the cell phone data. So it's obviously not perfect. Some of these areas right in Central Florida actually do a little bit worse in these probably more rural areas. And I think, I think one of the things that this so far is underscoring to me is that we might want to look at things as more an urban and a rural dichotomy. And I'm not totally sure how to do that. So here's just a few concluding sort of thoughts that I've had on these results. I have to say too that I'm very excited. This is the first sort of time that we've looked at these results in detail, and the first time I've talked about them. And even though these maps don't match up perfectly, they're really, really close, and they're closer than I think I would have guessed initially. So it's kind of nice to see. But so for the future work, I think I sort of have a few questions running through my head that people can comment on, and I see there are some things in the chat too, which maybe are related. But is how to make sort of an overall metric for these simulations. Because at first my thought was, well, we just say, okay, we have 10 counties that are white or that are perfect, and 20 that are bad, and 20 that are good. And so we then compare it to where all of them are bad. And then we could just compare it by the number of counties, right? Or by how different they are. But it might make sense to take into account that some of these counties have many, many more people. And so we might want to sort of weight these urban areas like Miami, more than these rural counties that have only several thousand people. So the idea being, in other words, since we're predicting the evacuation results of several million people accurately, does that count more? Does that make the simulation better than if it is predicting all these small 1,000 people counties, predicting their evacuation well? One of the key things that is next is comparing the results of this one storm, Irma, to others. If we can, and I'm hoping they do, if some of these results sort of scale over to other storms, that goes a long way to saying that this model is predicting, it is a good model in predicting the results, the behavior of people accurately. I admittedly need to just figure out how robust these results are. They are the result of only 10 simulations per result right now, and there's a lot of stochasticity in this simulation. So further work sort of needs to reaffirm the results. And this is one other sort of thing that these images have sort of made me think about, is whether or not it might be useful to identify a census factor that predicts particular counties well. So that over no vehicle did really well from the area around Miami. There could be some sort of combination of factors that is better at producing an overall prediction. And so I could see us modifying the simulation to try and use individual census factors for different counties if we can find that they do consistently predict the behavior of agents in a particular location well. So I'd like to thank you all for your time and invite you to ask questions. I definitely have a long list of co-collaborators to thank. So hopefully I've mentioned all their names as we were going through. But thank you all for your time, and I welcome your questions.
Well, thanks, Sean. That was extremely stimulating, and I particularly liked the arch that you spanned from archaeology to hurricanes. I have, to get us started off, I have sort of a more conceptual, almost epistemological question. How confident are we as a matter of principle that ABM models
Did Manfred just freeze?
the foresight that would be needed to basically better understand larger trends?
Manfred, I'm sorry, you froze in the middle of the question.
Yeah, I guess there was a internet connection. So the question is, how confident are you that we can turn the ABM factory that we are developing here into a useful toolkit for global futures related issues? I mean, the hurricane model is right there at the cusp of this. I think what you have shown is that for archaeological cases, given the data limitations that we have there, the ABMs really fulfill a gap that they allow us to see things where we don't have enough data, and we make reasonable assumption about behavior, and we can basically understand transitions in the past better that way. If we go towards the future, where we potentially could collect more data, and I think the way you demonstrated that with the inclusion of the cell phone data just shows this. Is the ABM still the right way to go, or do we have to switch to a different modeling strategy?
Well, obviously, as an agent-based modeler, I'm very confident in agent-based modeling, but I think for me, it's hard to imagine a modeling approach that incorporates location and geography as well. Because especially with the hurricane model, for example, so much is dependent on your physical location and environmental conditions that are specific to your location. And so I think in order to get that sort of global behavior, I think you need to model people sort of in their space. And I think, and that's what's drawn me to agent-based modeling in general. So much of archaeological data is spatially oriented, right? And so I think for me, at least, I think that's one of the strengths that makes it useful sort of for these future research.
Yeah, so I mean, I fully agree with you, and I think that what you mentioned in your answer, I think, is the key, because I'm thinking about it also from the point of view of strategic investment in the context of global future, and ultimately also the decision theater. And the point that you made about the location and the specificity of the context is something that ABMs have that other modeling approaches do not have to that extent. And therefore, a strategic investment in increasing the ability to build those larger scales ABM is really what we need. I think that's a very good answer that helps us make the case. And another sort of a technical issue, and I think discussion was in the chat, I think the question then becomes, how do we coarse grain the models so that we have an efficient modeling strategy? As you guys were saying, we don't need to model every single resident of Miami in order to get a reliable prediction. But that's also an interesting question about what is the right coarse graining.
You know, if I'm going to jump in, these results with the cell phone are really interesting in this respect, because it seems like maybe the reason that we're having less accuracy in rural areas is simply because we've had to coarse grain it too much. And those rural areas only have a couple of agents in them. And so there's much greater variance there, and greater potential for divergence from real world results. So somehow we have to optimize this coarse graining where it's not too much, not too little.
So, but then that means, Michael, that the coarse graining has to be dependent on, let's say, on the population density of the grid.
Could be, yes, something like this, yeah.
Yeah. Or the other thing is that essentially, my hope is that by running these models a lot more times, we'll be able to get a better image of those coarse grained areas, right? So they might be misrepresenting the people in that area once or twice, but the more times we run it, we hopefully should get a better picture of those rural areas.
Yeah. Yeah, maybe we need to run it 100 times instead of 10 or 1,000.
Yeah, we definitely, that's we start using the HPC a lot over the next few months.
I do want to point out to everyone that the colors are very faint because the differences between the real results and the model are actually very slight, you know, for most of the state, except for down at the far south, where just, I don't know what's going on down in the Keys, but it's weird.
Yeah, well, I mean, there are people in the Keys, but then a lot of that is the Everglades as well. And so no matter what, I mean, there's very few people down there. And then I suspect there are also interesting behaviors in that the Keys, you have to evacuate well before the hurricane gets there. And there's one road and in and out. It's this whole other sort of dynamic problem when you're living there compared to like if you're in Miami. So I think people might just tend to evacuate immediately if there's a hurricane, no matter what. They use a different logic.
Maybe it also has to do you know about the frequency with which they have been hit previously? So build a kind of a memory function into the behavior of the people.
You know, we've talked about that a lot in this project, and we really haven't, to my mind, come up with a good way of modeling that. Because you're right, people's past experiences with hurricanes play a large role, especially, you know, the common scenario that people will mention is, well, you know, they predicted this hurricane was going to destroy my house last time, and I was totally fine. So this time I'm going to be totally fine. They use this logic that the past is going to be a good model for the future. And I don't think we don't have a way of doing that. I guess not to my knowledge. We've talked about looking at sociological studies to understand people's preferences and how that information is used. But I don't think we've figured out a good way to, we haven't found the studies and we haven't incorporated it yet.
Okay, any other questions? Well, you're very busy on the chat, so articulate what you typed.
So I have a question. So a lot of times when we talk about simulation, when you talk about scenario planning and sort of strategic analysis, and I guess I was curious as to whether you guys have sort of, you know, rather than sort of testing model validity with these hurricanes that come through, but if we imagine climate change and hurricanes getting worse or whatever, a lot of times people just haven't quantified the uncertainty and like how bad things could get. And if you thought about using your sim not to sort of study hurricanes that have happened, but have studied the diversity of terrible outcomes that possibly could happen in the future to kind of give kind of an uncertainty cone, sort of a meta thing. You know, you don't really think about like, you know, a hurricane with an uncertainty cone in front of it, but it's almost like you've got this meta uncertainty cone of, you know, the uncertainty about uncertainty.
Yeah, I think so. I think that's sort of the next step, right? So because the way we're approaching things now is looking, okay, how can we accurately reflect people's decisions in the past to match up with these past hurricanes? And so I think that's the next logical step, yeah, is to take that, okay, now we have a good mental model of how people make these decisions. now let's, future cast it into a situation where there are multiple hurricanes or are more intense hurricanes than they're used to that form or that move in faster or less predictable, and see how people react.
So we've done a little bit of this, Ted, in that we've run the first series of experiments we're running to find out how people respond to different kinds of warning patterns. So that, if you warn people earlier, what happens? If you warn them later, what happens? So we did a number. We have a couple papers out that talk about some of these kinds of sensitivity tests. The difficulty in what you're suggesting is that we couldn't really do that well until we could find out how well the model actually predicted what people actually did. And we now finally have the data to be able to test that. So that's real exciting. And it turns out it's pretty good. What I put in the chat is that both the cell phone data, we know the proportion of people that evacuated each day of a hurricane, and we know the proportion of people in the county that we predicted would evacuate each day in the hurricane. And then we compare it to see which, how those proportions compare. Are they good or bad? And if you look at the color scheme on those maps, most of it is somewhere in the plus or minus 0.1 or 0.15 range. So I feel like that's pretty good for a first run on this.
Yeah, I guess to me, I guess I'm a little more optimistic about the use of modeling, in that, at least when we teach modeling, we talk about tests of sort of verification, and then at the validation steps, there's test of behavior, which I would argue is what you're doing now. But there's also the ultimate way you build confidence in modeling is in tests of learning. And a lot of times you can learn the actual validity of a model isn't as useful if it teaches you an insight, if it predicts an insight that you can get someone to try in the real world and it works.
Yeah.
So so that would be kind of an interesting thing if you said, like, you guys really don't know where to push out your messages first. And in the absence of any other model for how to do that, why don't you try our simulation model? And then they try it and it works really, really well. Even if your model doesn't match their numbers perfectly, it suggested an intervention that they weren't thinking about. And that happens all the time. So I mean, models don't have to be perfect to come up with great ideas.
So those were our first experiments, exactly like that, Ted. To say, if you were to do it differently, how would people respond to this? And then how would they be affected by a hypothetical hurricane if they responded in this way? Yeah, so I think it's really important.
Yeah,
and have people made those? Have you tried it? Like, have people actually altered the way in which they're doing these things and see how that worked out?
They don't think about it's very hard to get local hurricane people to do this because it's the local officials. I mean, they get the hurricane warning. Everybody gets the hurricane information from the same place, National Hurricane Center, and then it filters out through a bunch of different kinds of information channels, which we're trying to represent in this. And then there are county, local officials that actually make the call as to when they do something, and they have a history of this is how they do it, manuals and things like this. I mean, people at the National Hurricane Center and some other places are very interested in this so far, but so far we haven't been able to get it to filter down to the people who make the calls. I'm hoping that by doing the validation step that you're mentioning, which is what we're able to do now, we can convince more people that this actually might be useful to them. This is a hard thing to do for all of us in the modeling world.
Cool.
There's an interesting test case that, not for hurricanes, but remember those devastating floods last summer in Germany. And there is now a lot of work being done, sort of the blame game. But what they didn't pass on, because there were certain institutions who created a warning that was then filtered to local authorities who said, well, but for the last 100 years, that never was an issue that much. Mm-hmm. And so it might be worthwhile, too bad that Eric had to leave, because Eric has collaborators working on sort of decision structures in exactly that area. of Germany. So maybe there would be a way to collaborate with those and sort of show them your hurricane model and see whether this is something that they should adapt for their particular region in terms of floods. Because right now there is a lot of attention to this problem. And the name of Eric's collaborator actually reflects the region where the devastation happened. So this is sort of particularly amusing in that sense.
The way this model is constructed, it could be fairly easily ported to deal with flooding because the time frame is very similar to hurricanes.
That's why I say, you know, you have some better prediction that then sort of maps onto an outcome that should be used to guide policies. So it's the same logic.
Yeah. Whoops. Frozen again.
So I have a meeting with Eric in an hour, so I will tell him to get ask him whether they're.
You're freezing a lot there, Montford.
But yes, please tell Eric.
Yeah, tell Eric when you come back to on there.
There we
Okay,
go.
other questions? Well, if not, we are at our end time. You all know where and how to get in touch with Sean. So Sean, thanks again. It was a really informative overview of what you have been doing. And since communication over the last 2 years was limited, it was very refreshing to hear all of that in one package. So thanks.
Thank you, everyone.
Take care.
Bye.